My name is Henrik, and my title is Duck Racing, Estimating the Speed of a Swimming Duck. Have you ever thought about the wedge-shaped pattern that a moving object forms in water? Well, I did the other day when we were walking out in the park, and I took some pictures of the swimming ducks. I thought, I bet I could estimate the speed of those swimming ducks. And here we are. So why is this interesting then? Well, firstly, we tried to obtain some information from very little data. Here, in this case, only the angle of the wedge and the size of the waves. Secondly, we tried to measure or estimate the speed through quantities that at first sight don't seem to be closely related to the speed at all. And both of those points are highly relative to physics such as cosmology and particle physics, for example. So we approach the problem by first looking at the geometry. But we soon notice that we need some properties of the actual waves. For example, we need the speed of a moving wave crest. It's also called the phase speed or celerity of the wave. We do this by doing some fluid dynamics, and eventually we can apply this to our situation of the duck. So the geometry. We start with approximating the duck like a point. So we have a point source moving with the velocity v duck upwards, and this spreads out circular waves. During that time, a past wave translates with the speed vw to, say, the left, and thus we have this wedge-shaped pattern. And we have this relation between the two speeds. Now we only need to know vw. We do this by considering a cross-section of an ocean wave. Here we have a still water line at z equals to 0. We have the surface level displacement as eta, and we have the ocean depth to the bottom as d, and also a flow vector u, which could equivalently be seen as the velocity of a particle moving in the water. We have to make some assumptions, and we will start by assuming we have a small amplitude, which we will use later. We also assume that the waves are freely propagating, and that the water is incompressible and irrotational. This last point we use to get these equations for the velocity field. The divergence is 0, as well as the curl. And because of the second one, we can write a potential called the velocity potential phi. And when we insert this in the divergence, we get the Laplace equation for phi. We also need some extra conditions, and we start with boundary conditions. And the bottom first. Here we don't want any water to go through the bottom of the ocean, so we set the vertical component of u to 0 at z equals minus d. Also, at the surface, we don't want any water to go through the surface, so the velocity, the vertical component of the velocity equals that of the change of the surface level. We also relate the two unknown functions, the velocity potential phi and the surface displacement eta. And we use Bernoulli's equation for that, for irrotational flow, and that is essentially energy conservation. Here g is the acceleration of gravity. And now we use the assumption that we have small waves. So for the last two conditions we had, we linearize those and apply them to a still water line, because when we have smaller amplitudes, we can apply them instead at z equals to 0. After we have done this, we can explicitly solve for eta and find the phase speed of a moving wave as the following. VW equals the square root of g lambda over 2 pi tangent superbolicus 2 pi d over lambda. And this is from a book, Basic Coastal Engineering, by Robert Sørensen. Now to our actual swimming duck. In the pond, we actually have that the depth is much greater than that of the wavelength. So we approximate the tangent superbolicus as 1 and simply get this square root, which is highly inconvenient since we don't have to get our feet wet trying to measure the depth. Now we need to have an estimate for the wavelength as well as the angle. So I'd say that the width of a crest, wave crest, is approximately 5 centimeters, so the wavelength we get to 0.1 meters. And the angle we approximate is simply 90 degrees. Then we get the speed of a swimming duck using the geometry we had before and this expression for VW. We get the speed as 0.4 meters per second. And now we can compare this with actual measurements. So what we have here is on the x-axis the swimming speed of a duck, and on the y-axis the stroke rate, how much the duck moves its feet. We don't actually need the y-axis, we only try to see here on the x-axis, and as we see, our estimate of 0.4 is quite reasonable. And this is from a book, Readings in Animal Energetics, by another Robert H. Catlett. So, to summarize, we used the geometry of the problem to find a relationship between the two speeds. And we needed the speed of the water wave, which we got through essentially using Laplace equations, two boundary conditions, and energy conservation. We needed to do some approximations, like small amplitude, and that the wave was really propagating. But still, when we apply this to the swimming duck, we get a reasonable result. So, any questions? Thank you.
Questions to Henrik?
Dal?
I didn't get it. How did you estimate the optimal wavelength, or the wavelength of the wave that the duck produces?
Actually, from the photo, just estimating it's approximately 5 centimeters. So. Oh, the wavelength double that. Yeah.
Okay, so then I guess maybe that's kind of part of my question, but then using that, I guess that that's an average speed for a duck.
0.4?
Yeah. Like from your source, that would be an average speed for a duck.
Yeah, somewhat.
Okay.
So I just wanted to compare, is this reasonable? We did some very large approximations on our way, and we saw that, well, it's reasonable.
So,
yes?
Would it seem that the speed of the swimming duck doesn't depend too much on the drag of the water it's in, does it? The way you can describe it.
I don't see what you mean exactly.
Okay, so, I mean,
well, I'm just trying to figure out the speed it actually has from the pattern it makes in the waves, not how much it feeds flaps like he was doing here. Then the drag would matter, yes. Yes, Java?
I think there is some problem with the angle. If you want to measure the angles very exactly, you must
Be from above.
fly over.
Yes, yes.
Yeah.
That's why I had approximately 90 degrees.
There is some formula for you to
Project, yes.
just calculate.
Yeah. I was thinking of lying out rulers in 90 degrees as a coordinate system and photo of the swinging duck with these rulers in the picture, but I didn't have the time actually. Dal?
I think in the other room, Raul will present a very similar problem also for the duck, but he has an alternative theory.
Okay.
According to which the angle is always the same, independent of the speed of the duck. It sounds a bit strange, but he explained it to me. Unfortunately, I cannot reproduce it now because it was quite a lengthy argument. But
Okay.
if you want, I think his presentation is pretty good. Just start saying.
We could compare, yeah. That would be interesting.
Okay.
Thank you.
No more questions?